Welcome to Pratham Science Academy classes, and we are about to start on force and laws of motion chapter for class 9. And for this, our first topic would be force. What are the effects of force? Okay, in earlier classes, or in the previous classes, we have studied that force is the push or pull of an object. So we have studied this. The push or pull of an object is called force. Okay. But this is not actually the correct definition. And before we come on to the correct definition of the force, let's try to study the the effects of the force. What are the effects of the force? So whenever we apply a force on an object, what could happen to the object? Now, this force, this can, first of all, if an object is stationary, it can move stationary objects. So these are the effects of force we are studying so that we can arrive on the correct definition of the force. So it can move stationary object. That's the first effect of the force. And the second effect of the force, it can, if an object is, so if an object is stationary, let's say this object is stationary, and if we apply a force in this direction, this object starts moving. And if an object is moving, if an apply a force in the opposite direction, we can stop the object. So we can stop the moving object. And what could be the third effect of the force? The first two are can move a stationary object, we can stop a moving object, we can change the speed of an object. So how we can change the speed of an object? Let's say the object is moving. So either we can increase the speed of an object by applying more force, or we can decrease the speed of the object by applying the force in the opposite direction. So the third one is to change the speed of the object, and we can also change the direction of the force. We can change the direction of a moving body, not the force. But when we apply a force, we can change the direction of a moving body. And very good example for this would be when we hit a ball with a bat. Let's say this is the bat. When we hit the ball with the bat, the ball is coming from this direction. Hitting the ball with the bat means we are applying the force, and now the ball goes in the opposite direction. So in this way we can change the direction of a moving body with the help of the force or by applying the force, or we can also change the shape of a body. Let's say we apply a force on a plastic bottle, we can crumble that plastic bottle so it changes the shape of the body. So earlier we used to say that the force is the push or pull of an object, but now we have studied that force can move a stationary object, it can stop the moving object, it can change the speed, it can change the direction, it can change the speed of a body. So it's not just the push or pull of an object. So now our definition for the force changes, and now we are going to define the force. What would be the definition of the force? Now force is something, or force, let's say, is a physical quantity, and because it has both magnitude and direction, so it will be a vector quantity. The force is something which can physical quantity, or which can, it's not necessary that it will change, but it can change, or it can move. Let's say the first one was move a stationary object. So the force is a physical quantity which can move a stationary object, or it can stop a moving object, or let's say it can make moving object stationary, or it can change. So it was supposed to change the speed, direction, shape, or size of moving body. So now we have arrived at this definition. Instead of just push and pull, now we can say that force is a physical quantity which can move a stationary object, which can make moving object stationary, or change speed, direction, shape, or size of the moving body. So this is the correct definition, instead of saying that it just mere the push or pull of an object. Now let's try to solve one of the question that's mentioned regarding the force. And the question is, okay, our next topic is balanced and unbalanced forces. So we are going to see what are the balanced, or study what are the balanced and the unbalanced forces. So coming on to balanced forces. So what is balanced force? Okay, and to understand this, uh, let's take an example of a tug of war. So in a tug of war game, we apply a force. There are individuals on both the sides, and they are applying the force to get the rope on their side. So this is the force they are applying. Let's say this is the force F1 and this is the force F2. Now when the rope does not move, so that means both these forces are equal but in opposite direction. So both these forces are equal but they are in opposite direction, and the rope is not moving, so that means their net result, not the net force on the rope, is zero. So that is an example of the balanced force. So we can say that if resulted, so this is just an example of two forces. If there are number of forces, and if say if resultant, so in this case in the a tug of war game, the resultant of these two forces is zero. So let's say we have a number of forces acting at a point on this object. So these are the number of forces acting on this object. Let's say F1, F2, F3, and F4, and this object does not move. So that means the resultant of all these forces, that is F1 plus F2 plus F3 plus F4, is zero. So all these forces, that the resultant of these forces is the balanced force. So we can say that if resultant total of all forces is, and these all forces are acting on an object, acting on an object is zero, then this force, we call it the balanced force. So this is a balanced force. An example of this is tug of war game. So we can say that a tug of war game, but in this case, when both teams, they exert equal force. So that is an they exert equal force. That is an example of balanced force. And the next very good example of a balanced force is a stationary object. Now, how the stationary object is an example of the balanced force? Okay, let's say we have this stationary object, and let's say a box is kept on the ground. So this is a stationary object with a box that is kept on the ground. So this is the box that is kept on the ground. It is stationary. Now it does not move by itself and is stationary just because now the force of gravity is exerted from top to bottom. Let's say this is on the table. This is the force of gravity that is acting in the downward direction, and that is on the table. Let's say this is the table. Now in turn the table exerts equal and opposite force from, so this force of gravity is from, let's say, the top to bottom, and this may be a table or maybe a ground, and the force of reaction, this is the force of reaction the ground or the table exerts from bottom to top, and both the forces they balance each other. So these forces, the force of reaction and the force of gravity, they balance each other, due to which the object does not move or the box does not move. So this is an example of an balanced force. Now moving on to, before we move on to the unbalanced force, this balanced force, what could be the effect of the balanced force? Now the balanced force, its effect can be, it can change the shape and size. It can change the shape and size of an object. So we can say that whenever a balanced force and it is applied, it can change, ये change कर सकती है shape and size of an exam of an object. And a very good example of this is an inflated balloon. And if we apply force from this end and from this end, we can squeeze the balloon from both the sides and it changes the shape of the balloon. So the force that we have applied from both the ends is an example of the balanced force, and we can say now in this case we can say that balanced force can change the shape and size of an object. So balanced force can change the shape and size of an object. Moving on to the unbalanced force, the definition of this would be just the opposite of the definition of the balanced force, and in this case the resultant total of all the forces is not zero. So when the resultant total of all forces is not zero, we say that it is an unbalanced force. So this is an example of an unbalanced, this is a definition of the unbalanced force. Now, what could be the example of the unbalanced force? The first one is the force required to move a stationary object. The force that is required to move stationary object is an example of an unbalanced force. Okay, so in this case, why it's an unbalanced force? Because we push it with the force, and that force should be more than the frictional force. Now, because the force now is unbalanced, that is the muscular force, and this is an example of an unbalanced force. Now, the another example of the unbalanced force could be the force required to stop moving object. This is an example of an unbalanced force. This is the force required to stop moving object. Okay, another example of the unbalanced force could be when we try to change the speed of a moving object. That is also an unbalanced force. Now we have studied the balanced and the unbalanced force, and the summary says for the balanced forces, the net force is zero. So this is zero net force, And when there is no net force, that means there is no acceleration. And for an unbalanced force, the net force, there is a net force, it's not zero. And because there is a net force, so that means this can cause acceleration. Okay, so this was about the balanced and the unbalanced forces. Let's move on to the next topic. Thank you for watching.
Welcome to Pratham Science Academy classes, and in this video we are about to learn or discuss what is inertia and how this is applicable in Newton's first law of motion. So what is inertia? So this inertia is, we know that, okay, before that, let's say we have this object which is at rest. Now, this object will continue to be at rest unless and until some external force is applied on it. So if we push this object, it may move or will try to move or will try to move in the direction in which the force is applied. And let's say there is a moving object, let's say this car. Now this car is in motion and it will continue to be in motion unless we apply brakes and the friction. If this is the moving direction, then the friction acts in the opposite direction that stops the car. So in both these cases, this object will continue to be in rest unless some external force is applied. And this object will continue to be in motion unless this force of friction acts in the opposite direction. And let's say an object, let's say this ball, it's moving in this direction and we hit it from this side with a bat, and now it changes its direction to this side. So it will continue to move in the same direction unless we apply this external force and change its direction. So what we have learned here, that there is in all these cases there is a property, which is called inertia. So inertia is a property which is inherent in all those objects. So it is a property by which an object, or which we can say it is a property because of which or due to which an object will remain at rest or continue to be in motion or will continue to move in same direction. And this is happening till unless some external force is applied on it. Okay, so inertia is a property due to which an object will remain at rest or will continue to be in motion or will continue to move in the same direction unless and until some external force is applied on it. So this property of an object is called inertia, and we have the three types of inertia. That is the inertia of rest. So the property which keeps an object at rest unless some external force is applied is called inertia of rest. And the property which keeps an object in motion unless some external force is applied on it is called inertia of motion. And third one is the inertia of direction. So that an object will continue to move in a particular direction unless some external force is applied on it to change the direction. So we have three types of inertia: inertia of rest, inertia of motion, and inertia of direction. Now let's consider some daily examples where these inertia is applicable, or we can find the use of the inertia. The first one is when car suddenly stops or starts, passenger moves backwards. So the first we can say the application is when car, and we will see what type of inertia it is. The first one, the second one, or the third one. So the when car suddenly starts, you might have experienced it that we fall backward. So when car or the bus suddenly starts, passenger fall backwards. So why is it so, and or what is the reason for this? So when the car suddenly starts, let's say like this is a car and the passenger is sitting in the car. Let's say this is the lower part of the passenger or lower part of the body. Now, when the car suddenly starts, the lower part of the passenger is in contact with the floor of the car. So, due to inertia of motion, this or when the car starts, this part, the lower part will come in motion as it is in contact with the floor of the car, but the upper part will continue to be in rest because of inertia of rest, and hence we fall backwards. So that is the reason. So we can say that when car suddenly starts, the lower part of the body. So when car suddenly starts, we can say the lower part of body which is in contact with the car comes in motion, which is in contact with car, it comes in motion. But the upper part, it will continue to be in rest because of inertia. And hence we can say that hence we fall backwards. So this is, in this case, we have to mention that this is because of inertia that we fall backwards. So the next example is when the brakes are applied, passenger are pushed forward. So this is the first example, first application, or let's say the use of inertia. And the second one is when car or bus brakes are applied, let's say the bus. So when the bus brakes are applied, passengers fall forward or get pushed forward. So in this case, it's the same reason. Let's say this is the lower part of the bus where the passenger is in contact with the lower part, the lower body. This is the lower body, the lower part of the body, and this is, let's say, the upper part. Now, when the brakes are applied, because the lower part is in contact with the floor of the bus, this part will come to rest, but this will continue to be in motion, hence we fall forward. So this is because of the inertia as well. So we can write here, or we can give the explanation that when car or bus suddenly stops, the lower part which is in contact with the bus, this comes to rest. But due to inertia of motion, this upper part of our body, it continues to be in motion, hence we fall forward or we are pushed forward. So this is because if we fall forward. Now next, a very good example would be when we beat a hanging carpet with a stick, dust falls off. So what is the reason for that? So this could be the third case, and we can say that when this hanging carpet is beaten with stick, dust falls off. So what is the reason? Okay, let's say this is the carpet and we have dust on this. So when we beat the carpet with a stick, so this is pushed backward. But because of inertia, the dust particles will continue to be in rest, and hence they fall downward. So this is the reason when the carpet is beaten, which comes in motion. So let's say when carpet is beaten, this is the reason it comes in motion, but the particles are at rest because of inertia. And hence the dust falls off due to gravity. It will fall downward due to gravity, will not go upwards. The dust falls off, or let's say downwards. So because of the force of gravity. So this is what is inertia, and these are the very convenient examples that we can show off. And one example more we can cite here is when a tree is shaken vigorously, its fruits or leaves they fall down. The reason here is same. When a tree is shaken vigorously, its fruits and the leaves they fall down. The reason for that is when a tree is shaken, it comes in motion. And when the tree comes in motion, but still the fruits and leaves they remain at rest due to inertia, but leaves and fruits. So this is how you have to write an answer for this. Make sure to mention due to inertia in the answer, and thus they fall off, fall down to the ground because fall off due to, and the reason here is due to gravity. So we can explain this. Okay, some more examples we can also uh, give here for the inertia is that when a car takes a sharp turn, we tend to fall sideways. So this is one more example which can be asked for the reason. So when a car or bus that takes a sharp turn, we fall sideways. So, okay, let's say this is a sharp turn and we are in this car. Let's say this is the car and we are sitting here. The car comes here and we fall sideways towards this side. So that is also because of the inertia. And the reason is that when the car or bus takes a sharp turn, the lower part of the body, which is in contact with the car, also takes a sharp turn. So here, the lower part, which is in contact with, this is the lower part of body, which is in contact with lower part of car or bus. This also takes sharp turn. So because the car or the bus is taking a sharp turn, our lower part of the body will also take the sharp turn, but upper part is still moving in a straight line. Or we can say that upper part continues to be in a straight line, and this is because of inertia. So upper part continues to be in straight line due to inertia, and hence we, or let's say the passenger, they fall sideways. This is how you can explain the reason for this. And we can also get one more example for this. That is, it is dangerous to jump out of a moving bus. Why? So this, it is dangerous to jump out of a moving bus. And what is the reason for this? So let's see, this are six use of the inertia or the application of the inertia. So why it is dangerous? Okay, let's say this is the bus which is moving, and suppose this is the passenger. So when the bus is in motion, so this passenger is also in motion when he jumps out of the bus, and let's say he falls on the ground. Now the ground is in rest, it's at rest, and as soon as his lower body touches the ground, the lower body comes to rest, but the upper part still continues to be in motion, and hence we fall. So, and may get hurt. So that's why it's dangerous to jump out of a moving bus. And the reason we have mentioned here is that when we jump from a moving bus, so when we jump, so our feet comes in touch with the ground at rest, but our upper body, it continues to be in motion, and hence we may fall on the ground and get hurt. Hence, you can see that. Okay, so these are some of the applications or the reasons where we can cite examples for the different types of inertia. So by this time, we are clear that what is inertia and how this plays an important role in our day-to-day life for some of the applications. Okay, now which objects will have more inertia, the heavy one or the light one? Let's try to. So now the question arises, which object So which object had more inertia, the heavy or the lighter one? Okay, so in this case, more is the mass, more is the inertia. So heavy objects have more inertia than lighter objects because let's say we have two objects, one of mass 30 kg and one of mass 10 kg. So it would be difficult for us to move an object with more mass. So more is the mass. It's difficult to move this object. So that means that it will tend to remain in rest. So that means the more will be the inertia. So heavier objects, more is the mass, more is the inertia. So heavy objects have more inertia than lighter objects. So we can say that more is the mass, more is the inertia. Or we can say that mass is the measure of inertia. Inertia, sorry. Okay, so mass is the measure of inertia, more is the mass, more is the inertia, and with this we are done with the with today's topic for inertia and its types. Let's move on to the next topic. Thank you for watching. Welcome to some Science Academy classes, and in this video, uh, we are going to discuss what is Newton's first law of motion, and we will try to apply it in some cases in the real life scenarios. So, the Newton's first law of motion is also called law of inertia. Now, in the previous video, we have discussed what is inertia. Inertia is property of an object by which it continues to remain in state of rest or continues to remain in state of motion or will not change its direction unless and until some external force acts on it. And that is exactly the Newton's first law of motion. So Newton's first law of motion states that, so we can write that it states that object will continue to be in rest or we say that object will continue to be in uniform motion in a straight line. Object will continue to, let's see, to be in the uniform motion we have already discussed in previous chapter. When an object covers equal distance in equal intervals of time in a straight line, we say this is in uniform motion. So the object will continue to be in state of rest or object will continue to be in uniform motion and here it should be in a straight line unless, so this is possible only unless and until some external force acts on it. This is what exactly was discussed in inertia. So that's why we call Newton's first law of inertia as well. Now let's consider an example. Let's say this is a block on a surface which is stationary. So this is stationary, and when we apply a force from this direction, this will start moving in this direction. So this will continue to remain at rest unless some external force acts on it. So this is the first example where a block or an object at rest will continue to be in rest unless some external force acts on it. So when external force is zero, this object will continue to be at rest. Next example would be, let's say we throw a ball on the ground. Let's say this is the horizontal ground and we throw a ball on the ground. We apply the force from this direction, and after some time the ball will come to rest because the force of friction is stopping the ball. So unless and until some external force, so this is the external force that stops the ball, moving ball. This is the external force that keeps the stationary object moving. So this is the Newton's first law of motion, which is also called law of inertia. So basically it exhibits the inherent property, that is the inertia of rest, inertia of motion, and inertia of direction. So unless and until some external force acts on it, the object will continue to be in rest or will continue to move in a straight line. Here the force which stops a moving object is force of friction. So this is the Newton's first law of motion, and let's move on to the next topic. Thank you for watching. Okay, so in this video we are about to discuss what is momentum and uh, what would be its effects on the heavier or the lighter object, and some more uh, questions regarding the momentum. Okay, so first of all, momentum. We know that, let's say whenever an object, let's say this is a mountain and there's an object on the mountain, so it rolls down and comes into motion. And this motion was already contained in this object. So we can say that momentum is the quantity of motion contained in an object. So it is a physical quantity we have given. We are trying to find the magnitude of the quantity of motion in a body, and let's see what all factors it depends on. And so momentum is, in simple layman's language, is the quantity of motion contained in a body. So, because the bodies are lighter and heavier, so that means the quantity of motion will also be less or greater in the body. So let's say how we are going to check if the quantity of motion is more or less in a certain body. So, quantity of motion contained in a body is called momentum. Now, it is, how do we measure this? Because it's a quantity of motion, so we have to measure this. So it is measured as the product of mass and velocity. So because we are measuring it, we have to denote it as well. And it is denoted by small letter p. P. So momentum is small letter p. Now we have to measure it is the product. So P is the product. Momentum is the product of mass, which is denoted by M, and velocity, which is denoted by V. So momentum is equal to mass into product of mass and velocity. And from here we can write down its SI unit as well. SI unit of mass is kg from the formula itself, or and the velocity is SI unit is meter per second. So the SI unit of momentum is kg meter per second. Okay, now momentum will be higher for heavy object or light object. It's very obvious from the formula because momentum is measured as the product of mass and velocity. So let's say we have an object with both are moving with the same velocity. So let's say they are moving with the velocity of 10 meter per second, but here the mass of the first object is 10 kg and the mass of the second object is, let's say, 20 kg. So the mass of the, so momentum of the first object, that is object A and object B. B is heavier, so momentum of the object A would be m1 into V. Velocity same, so let's consider it as a v, which is equal to 10 into 10, that would be equal to 100 kg meter per second. Now let's calculate the momentum of the second object, which is m2 into v. Mass of the second object is 20, velocity is same, which gives us 200 kg meter per second. Do remember to put in the SI units. Okay, so mass, so the momentum of the heavier object is more as compared to the momentum of the lighter object. So we can say more is the mass, more is the momentum, or we can say that momentum is directly proportional to mass of the object. So heavier object will have higher momentum and the lighter object will have lower momentum. Okay, so whose momentum is higher, an object at higher speed or lower speed? So in this case, let's consider the same example. Let's say this is an object A, this is an object B. Now we have to vary the speed. So let's say mass of both these objects is 10 kg. So mass is same, so I'm going to keep it as m0, m1 and m2. Now, the velocity of the first object is, let's say, 10 meter per second, and the velocity of the second object is, let's say, 20 meter per second. Let's calculate the momentum in both the cases. It's m into v1, which is equal to 10 into 10. That is equal to 100. And what is the SI unit? Kg meter per second. Let's calculate the momentum in this case. So this is m into v2. Mass is 10 into 20, which gives us 200. Don't forget to put in the SI units at 200. So the object with the greater velocity has greater momentum. Object with lower velocity has low momentum. So higher the speed, higher is the momentum. It's obvious from the formula because P is equal to m into V, and keeping the mass constant. If we keep the mass constant, it gives us P is directly proportional to V. So that means more is the velocity, more is the momentum. Okay, now what do you get after the change in momentum, or what is change in momentum? Before we move on to what is change in momentum, let's see what is change. So change is actually the final value minus initial value. Okay, now how do we find the change? Let's say a student scores in physics in, let's say, first term, he scores out of 30, he scores 20 marks. And in the second term, out of 30, he scores 30 marks. So this is the final score, and this is the initial score. And what exactly is the change? So change will be final score minus initial score. So final score is 30 minus 20, which is equal to 10. So 10 is the change, is how we calculate the change by subtracting the initial value from the final value. So if we have to find the change in momentum, so instead of the score, we will write, we are going to find the change in momentum. For that, we need the final and the initial momentum. So that would be final momentum minus initial momentum. Okay, what would be the final momentum? We know that momentum is given by P is equal to m into V, and usually we use V for the final velocity. So for final momentum, it's m into V final velocity, and if we have to calculate, this is the final momentum. And if we have to find out the initial momentum, so we will have, because mass will be constant, we just change the velocity, so that would be initial velocity. So initial velocity will m into u, and m is common, so we will write m into v minus u. So our change in momentum, it's mathematically written as m into v minus u. Okay, so this is change in momentum. How do we find calculate the change in momentum? Next is the rate of change of momentum. Okay, we know that the change in momentum, is given by final momentum, which is mv minus initial momentum. Now, what is rate means the rate of change of momentum means we have to divide the change in momentum by time. So whenever there is a rate, you have to divide the change by the time. So change in momentum is given by m into v minus u and time is t. So v minus u by t, we have already discussed it in motion chapter. It's change in velocity. Rate of change of velocity is acceleration. So instead of v minus u by t, we are going to replace it by a, and that m into a we know that m into a is the force. We are going to discuss this later on. So for the time being, let's just keep that m into a change rate of change of momentum is m into a, and which would be equal to force. We will discuss this in the next video. So for the time being, what is momentum is the quantity of motion contained in a body. It is measured as a product of mass and velocity denoted by p. Formula is mathematical expression is m into v, assign it is kg per second. P is directly proportional to m. That means more is the mass, more is the momentum. P is directly proportional to v, more is the velocity, more is the momentum. And change in momentum gives is mathematically written as m into v. It's given by final minus initial momentum, which is m into v minus u. At rate of change of momentum, whenever there is rate, you have to divide the change by time, and change in momentum is given by v minus u. If we divide it by dv minus u by d is a, and m into a is f, which is the force. Okay, so we are done with the momentum, and let's move on to the next video. To like, share, subscribe. Thank you for watching. Welcome to Pratham Science Academy classes, and in today's video we are going to discuss Newton's second law of motion and what are its applications. So, what is Newton's second law of motion? Let's uh, write down its definition first. And the Newton's second law of motion has mathematical expression as well. So we'll derive its mathematical formula as well. That is a mathematical expression. So firstly, then it's the definition. So it states that the rate of change of momentum is directly proportional to the applied unbalanced force, and it takes place in the direction of force. So that's the definition. So that is, we can say that the Newton's second law of motion, it states that the rate of change of momentum, we will also find out or derive its mathematical formula and hence define 1 Newton. So it states that the rate of change in momentum, which we denote by P of a body, is directly proportional. That is, this is a sign for the directly proportional. Is directly proportional to applied force. That is, the force should be unbalanced, or we can write it as with more specific as unbalanced force. Right. Okay, and it takes place in the direction of force. It's obvious. Okay, so this is the definition of the Newton's second law of motion, which states that the rate of change in momentum of a body is directly proportional to applied unbalanced force, and it takes place in the direction of the force. Let's try to get and its mathematical expression. Let's try to derive its mathematical expression, and hence we will define the SI unit of force. So the derivation of Newton's second law, or the mathematical expression, we can say Okay, now from the statement, it's given that the force is directly proportional to rate of change of momentum. Okay, that means this unbalanced force is directly proportional to rate. Change in momentum is given by the final momentum minus initial momentum, and rate means it has to be divided by the time. Okay, now the final momentum, we know that the momentum is denoted by P for final momentum, and the formula for the momentum is P is equal to M into B. For final momentum, let's take the final velocity, and for the initial momentum, that would be equal to M, or that is mu, and for time it's T. Okay, so this becomes F is directly proportional to, let's take M common, V minus U by T. Now we know that change in velocity, that this is the rate of change of velocity. Change in velocity divided by time is rate of change of velocity, which is equal to acceleration. So we can write it's directly proportional to M into A, and this is constant. So it becomes equal to, and let's put in some constant here. If you remove the proportional sign, that would be equal to M into A. And this k is the constant of proportionality. If you put k is equal to 1, our mathematical formula from the Newton's second law becomes F is equal to M into A. Now, this is the mathematical expression of Newton's second law of motion. From here, we are going to derive the SI unit of force. Now, if let's say mass is 1 kg, and so this mass is 1 kg, and acceleration is 1 meter per second square in SI units. So this is 1 meter per second square. So this force becomes 1 into 1 is 1, so 1 kg meter per second square, and we call it as 1 Newton. So kg meter per second square is denoted by Newton. Now we have the SI unit of force, that is Newton, and we are going to define 1 Newton. So 1 Newton, so we say that, what is the definition of 1 Newton? So we say that force, because it is the SI unit of force, so we will say force is said to be 1 in Newton when it it means force produces an acceleration of 1 meter per second square in a body of mass 1 kg. So that's the definition of 1 Newton. So the question here is, state Newton's second law of motion and derive the mathematical expression for it, which is equal to F is equal to M into A, and hence define 1 Newton. So this is the Newton's second law of motion. This is also called the real law of motion, and why it's called the real law of motion, we will discuss that once we have studied the Newton's third law as well. Okay, so let's move on to its applications. So our first application is why a fielder pulls his hands backwards while fielding the ball. So you might have watched the cricket match, and in that you might have noticed that whenever a fielder tries to catch or fields a ball, he takes his hands backwards, and there is a reason behind it. That is the application of the Newton's second law of motion. So fielder does this to increase the amount of time while catching a ball. So he, by pulling his hand backwards, he's increasing the time. So fielder is increasing the time, and what happens when the time is increased by, so fielder is increasing the time to catch, or the time of impact of the ball on the hand. So he's increasing the time while catching a ball. And why he's doing so? So while he pulls his hands backwards, he is increasing the time to catch the ball. And when the time, because we know that the force is directly proportional to rate of change of momentum, that is m into v minus u by t. And by increasing this time, we are reducing the rate of change of momentum. This value becomes small. And when this value becomes small, which is directly proportional to the force, the impact of the force is small. So let's try to understand it in this way. Let's say the time is 5 seconds and the rate of change of momentum is 2, so the force is 2 Newton. Now, when we increase this time, let's say we increase this time by 10 seconds. So if we increase the time, so now the force is 1 Newton. So here, when the time is increased, the rate of change of momentum reduces and the force, it also reduces. When the time is less, the rate of change of momentum increases and hence the force is more. So in this case, it may hurt the hands of the fielder, but in this case, because the force is less as the time is increased, rate of change of momentum reduces. So that's why the impact of the force will be less and hence the hands may not get injured. So in this case, we can say that whenever a fielder catches a moving ball, it actually brings the ball. So if let's say the fielder does not pull his hands backwards. So the reason here is that fielder is increasing the time while catching the ball, and which this reduces the rate of change of momentum and applied force. So this reduces the change of momentum, and when this rate of change of momentum is reduced, it reduces and hence force is less. When the force is less, there are less chances of getting hands injured. So there are less chances of getting injured. However, however, let's say the fielder stops the ball. He does not pulls his hands backwards and immediately stops the ball. So in that case, the he's trying to, let's say this is the ball. It's coming towards the fielder's hands, and these are, let's say, the fielder's hands. So he's not pulling the hands backwards. So he brings the velocity of the ball. So this is, let's say, there is some initial velocity. The ball is coming at a speed of 30 meter per second. So by catching the ball and not pulling the hand backwards, he's getting the velocity or reducing the velocity of the ball to zero in a very short time. So this is short, which increases the change in momentum and hence it increases the force and he may get injured his hands. So that's why a fielder pulls his hands backwards while fielding the ball to increase the time while catching the ball, which reduces the change of momentum and hence the force is less and there are less chances of getting injured. Let's move on to the next application of the Newton's second law of motion. Why a high jumper is provided cushion or heap of sand on falling. So reason here is same. So a cushion or a heap of sand is provided to prevent injury to the athlete whenever he falls down after making a high jump. So when athlete falls, let's say this athlete falls on cushion or heap of sand. So now the whenever he falls on a cushion or a heap of sand, this jumper takes a longer time to comes to rest. He takes more time to come to rest because with him, the whenever he lands on the cushion or a heap of sand, so let's say this is the cushion. So whenever the athlete lands on this, so whenever he lands on this with him, the cushions are pressed, and this increases the time for the jumper to comes to rest. And so he takes more times to come to rest, and by doing this, the rate of change of momentum of athlete is less, so which reduces the rate of mm, change of momentum. Now the rate of change of momentum is reduced. So now the rate of change of momentum is reduced. That means smaller stopping force acts on the athlete. So we can say that smaller force, and because it's acts on athlete. Now because the smaller force acts on athlete, so the athlete doesn't get hurt. Okay, so that's the reason a jumper is provided with cushion or heap of sand instead of the mud, or let's say the concrete, because when someone falls on a concrete, it takes less time to come to rest. Rate of change of momentum is in that case increased. Larger force acts on athlete and athlete gets hurt. So this is the second, we could say, the application. Okay, how seat belts prevent injuries in car. So how seat belts prevent injuries in car. So let's say in a car accident, what happens in a car accident? So in an accident, so this car strikes some another vehicle or some other obstacle, and a fast running car comes to rest immediately. So this fast running car, this comes to rest in a short time. Okay, so due to this, the large momentum of the car reduces to zero in a very short time. So due to this, because the time is less and the large momentum happens, large momentum is reduced to zero in a very short time. And now when this happens, the seat belts that is worn by the passengers increases the time taken by the passengers to fall forward. So what are the belts doing? So belts, so seat belts, they increase, if they are worn by the passengers, they increase the time taken by the passengers to fall forward. Okay. Due to this, now the for seatbelt increases the time taken by the passengers to fall forward, and because of this longer time, what is going to happen? The rate of change of momentum is reduced. So there are two cases. The fast car is in an accident. The fast running car comes to rest. Its large momentum is reduced to zero in a very short time. Now the seat belts, because of this large momentum is reduced to zero in a very short time, there is a large impact on the passengers. If they're not wearing the seat belts, they may get fatal injury, and the seat belts, they increase the time taken by the passengers to fall forward. Due to this longer time, the rate of change of momentum is reduced. So the rate of change of momentum is reduced in a long time, this results in low or lessening. We say no or lessening. So that's why the seat belts are provided in to prevent the injury in the cars. Okay, now our last application would be how a karate player breaks slab of bricks in a single move. Okay, here it's because of the very high amount of momentum produced in a very short span of time. So let's try to explain this now. When the hands of karate player moves, they carry velocity. When the hands of this karate player moves, so what are they trying to do? Okay, so the hands of the karate player moves, and you might have seen that they bring down the hands with a very large velocity. So the when the hand touches the, let's say, the slab of bricks or the ice, the velocity is brought down to zero in a very short span of time. So we can say that when the hands touch the slab, the velocity is brought down to zero. Zero with a large amount of momentum in a very short span of time. So what is happening? The hands of the karate player moves very fast, or let's say with high velocity. Comes down with high velocity. And when the hands touch the slab, the velocity is brought down to zero with large amount of momentum in a very short span of time. So because of this very short of span of time, the rate of change of momentum is increased, and hence the unbalanced force, and hence we can see very high unbalanced force. This breaks the bricks or the slab. We can see the slab of the ice or the bricks. Okay, so this is how exactly the karate player breaks a slab of bricks in a single blow. So we are done with the Newton's second law of motion and applications. Do like, share, and subscribe. Thank you for watching. Welcome to Pratham Science Academy classes, and in this video we are about to start with Newton's third law of motion. So what is Newton's third law of motion? And we are going to note down some important points regarding this. So Newton's first law of motion states that uh, when one object exerts a force on the other object, let's say this is an object that is lying on horizontal, that is ground. So this is the ground and this is an object. So this object is applying force, which is weight on the ground. So we call it as an action. So in turn, this ground also applies force in the opposite direction, and we call it the reaction. And both these forces are equal. Both these forces, this reaction is also equal to W. So this W is the weight, that is the force, and we know that weight is a force within an object that is attracted towards the center of the earth. So this object is attracted towards the center of the earth and it applies the force on the ground, which we call weight. And in turn, the ground applies equal and opposite reaction in the opposite direction. So this is exactly what is Newton's third law of motion. So we can say that as per Newton's third law of motion, okay, so Newton's third law of motion, the first, there is one object. So when one object exerts a force on other object. So this is the first case. Now in turn, the other object, it also exerts an equal and opposite force on first object. So this is Newton's third law of motion. So we have to remember some important points regarding this Newton's third law of motion. The things that are to be noted is that, first of all, there are two forces, and one force is called action. So there are two forces. First force, one force is called action. So this is the action and this is the reaction. So one force is called action and the other force is called reaction. So this other force is called reaction. So we can say that for Newton's second law, it's the action and reaction. These are the two forces, force 1 and force 2. These are equal and opposite. So this is the first point that is to be noted now. The second point is that both the forces are in opposite direction. So both the forces are in opposite directions. That is a point that is to be noted. And both forces act on different bodies. So the action acts on ground and the reaction acts on the block on the ground or the object on the ground. So we can say that both forces they act on different bodies. So this is the third point, and now we had already mentioned that both forces are equal. Okay, so both the forces are equal. However, if they produce an acceleration, the acceleration may be different. We are going to explain this force part. So acceleration may be different. Now, well, let's see. So acceleration is different because the mass of two bodies are different because of different masses of two bodies. Okay, let's say this is a block and this is resting on the table. Mass of the block is m1 and mass of the table is m2. So let's say mass this block A and table B is applying the force F1. So FAB is the force applied by the object A on B, and FBA is the force applied by the object B on A. So these forces are equal but in opposite direction. So this force FAB is in downward direction, and the force on object this is a force applied by object A on B, and this is a force applied by object B on A. In the upward direction, both these forces are equal and opposite. Now we know that the formula for the force according to Newton's second law is m into A. So for this, it is a force applied by object A on B, so mass of object A into the acceleration. This will be the acceleration of first body. The force of one body, this is the mass of first body, force of one body. So this is the force applied by object A on B. So this is force is applied on object A on B. So this is the mass of object A into the acceleration of second body. Now this is equal to negative. Negative is for the in the opposite direction. This is the force applied by B on A. So this is m1, that is the mass of the first object, into acceleration of first body. So in this case, if now if mass of first body, this m1, is greater than m2, then the acceleration of first body, if m1 is greater than m2, then acceleration of first body will obviously be less than acceleration of second body. And if m2 is greater than 1, then acceleration of second body is less than acceleration of first body. So this is how the acceleration may be different because of different masses of two objects. Okay, let's consider some practical examples of the Newton's third law of motion. And the first one is walking. So we are able to walk because of Newton's third law of motion. So walking, so when we walk, so let's say this is our feet. And so when we walk, our feet, it's now like this, and it exerts a force in the backward direction, and in turn the ground pushes us forward. So we are able to walk because of the Newton's third law of motion. So when we walk, our feet exert a force on the ground, on ground, which is action. And this force is in backward direction. Now in turn, the ground exert a force in forward direction, and this makes us move forward. So that is how we are able to walk. And next example we can consider is jumping to land from boat. So we are jumping from the boat to land on, let's say, from, okay, let's consider this is a boat in the water, and here is the land. So a person is about to jump from here. So when he jumps from to the land, he a sailor jumps from the boat, so he exerts a force on the boat in the backward direction, and the boat gives equal and opposite force in the forward direction. This makes the person get out of the boat. So the first one here is that person exerts a force on the board in backward direction. So the two objects are the person and the board, and this force is called action. And in turn, this board exerts equal force on man, let's say the sailor in forward direction, and this makes man jump out of the boat. Okay, there can be other examples as well, and let's consider this colliding of two football players. Let's say the two football players collide and both get hurt. So colliding of two football players. Let's say these are the two football players A and B, and when both these collide, both of them hurt because when they collide, A exerts force on B and B exerts force on A, and both of them get hurt. Okay. Again, the most important one is the recoil of a gun. So you might have seen that whenever we fire a bullet from a gun, it pushes us back, pushes us in backward, and these forces are equal and opposite. But the bullet moves with a greater velocity, and we are not pushed backward with an equal acceleration with the greater acceleration because our mass is greater. So when a gun is fired, we will discuss this later on in the law of conservation of momentum. So when a gun is fired, so it exerts a force on bullet and bullet comes out with greater velocity. It exerts force on bullet in the forward direction. So bullet also exert equal and opposite force in the backward direction. So that's why we keep the gun close or tied to our shoulders. So this is, let's say, the gun, and this is the trigger. It's a bullet inside, so it comes out with great velocity, and in turn, the gun is also pushed backwards. So that's why we keep this gun tied to our shoulders, so that because if there's a gap between the gun and the shoulders, then the force with which it comes backwards will hurt our shoulders. So that's why we keep it tied to our shoulders. Okay, so these are the examples of the Newton's or the applications of the Newton's third law of motion. Okay, let's move on to the next one. Do like, share, and subscribe. Thank you for watching. Welcome to Pratham Science Academy classes, and in this video we are about to start with the law of conservation of momentum. This might have been deleted from the syllabus in 2025. So What is law of conservation of momentum? Before we do that, we know that momentum is the quantity of motion contained in a body, and it's denoted by P, and it's measured as the product of mass. So law of conservation of momentum says that, let's say, uh, when two or more bodies they act upon each other, total momentum remains conserved. So that is law of conservation of momentum. So we can say that when it's just two, we will also to try to prove it, the law of conservation of momentum. So when two or more bodies they exert force on each other, or they act upon each other, they exert force on each other, total momentum remains conserved. We will try to it as well. So total momentum remains conserved. That is, and provided here the condition should be no external force. So no external force is acting on the system of two bodies. So two or more bodies. So when two or more bodies they exert or act upon each other, total momentum remains conserved, provided no external force acts on the bodies. So when no external force acts on the bodies, it means it's an isolated system. So we can write it as well. It can be written in another way, or isolated system means when no external force is acting on a system of bodies, whether it may be two or more than two. For an isolated system, total momentum remains conserved. Okay, let's try to prove it as well, how the total momentum of the two bodies or the system of two or more bodies remains conserved. Let's say there are two objects A and B. So we are about to derive the law of conservation of momentum. So we have these two bodies. Let's say this is object A and this is object B. Okay, and they interact with each other. Let's say they collide with each other. So this is the system before collision, and let's say mass of this body is m1, mass of object B is m2, and it's moving towards the B with initial velocity u1, and it's moving towards A with initial velocity u2. So here this is the situation before collision, and now let's say these two bodies collide. So now the collision, because they are moving towards each other, so these two bodies will collide, and A will exert force on B and B will exert force on A. Let's say these bodies they collide for an instant, and after collision they will during collision they will object on A will apply force on B and B will apply force on A. So what will happen after collision? So after collision they will move either away from each other or may get deflected in a particular direction. So let's say after collision, their velocity will change. Okay, now this object E, they collide and are deflected back. So this moves with final velocity v1 and this moves with final velocity v2. Their mass remains same. So this is the situation after collision. Okay, let's try to calculate the forces. Now, let's say the force on object A, force on object A. We know that the force is given by mass into acceleration. So after collision, let's say this it moves with acceleration a1 and this moves with acceleration a2. So the force on object A will be m1 into a1. Okay, now the acceleration. We know that acceleration is the change in velocity. So for object A, its final velocity is v1 and initial velocity is u1 by t. Okay, now let's calculate the force on object B. Force on object B will be F is equal to m2 into a2, which will be given by m2 into this will be v2 minus u. Okay, this is the force on object B. Let's say this is force on object A by B, force on object B by A. Okay, according to Newton's third law of motion, action and reaction are equal and opposite. So we are going to use the Newton's third law of motion. And according to Newton's third law of motion, action and reaction are equal and opposite. For opposite, we put in the negative sign. Let's now write down the two forces. So this is m1 into v1 minus u1 by 2 is equal to m2 into v2 minus u2 by t. So t and t gets cancelled. And let's open up the bracket. So this is m1 v1 minus m1 u1 is m2 v2 plus this is m2 u2. Okay, now let's get these v1, the final velocity on one side. So this is m2 v2 and this is now m1 u1. So I'm moving this to this side and this to the right hand side. So m1 u1 plus m2 u2. Now this m1 v1 is the final momentum of object 1 and this is the final momentum of object 2. So this is the final momentum of the system A and B. So since the final momentum of two objects we can write, so this is the final momentum of two objects and this is the final momentum. Sorry, this is the initial momentum because we have this is the initial momentum of the first object, this is the initial momentum of the second object. So this is the initial momentum of two objects. So final momentum of two objects is equal to the initial momentum of two objects. That is what exactly is the law of conservation of momentum. So we can say that momentum is neither created nor destroyed, but it remains conserved. So momentum is neither created nor destroyed, but remains conserved. So that we have also proved it. So this is the law of conservation of momentum. Do like, share, and subscribe. Thank you for watching.